Drawing in three-dimensional space. When we draw in 3D space for Calculus 3, we make the axes as you see on your screen, where very often the axis that looks like it's at an angle is the x-axis, and the one off to the right is the y-axis, and the one standing straight up is the z-axis. So when I'm trying to imagine more complicated shapes that we'll get to in later videos, or just when I'm in class trying to teach Calculus 3, I imagine the floor as being the xy plane. And then the z is the height above or beneath the floor. But let's just start by drawing some very basic shapes or other things. In fact, let's start simply by plotting the point 2, 3, 4. And I'll show you how I would draw it here. So we would do 2, 3, 4 being x, y, z. That's a standard order that we would write things in. So this is saying we're going to go 2 down the x-axis. Now the axes that I've drawn are the positive axes. So I'm going to go 1, 2 down the x-axis. And then I need to go 3 down the y-axis, so 3 down the y-axis. So let's just get that part first. The way I usually draw kind of other things or something that helps me draw is I stay parallel to the lines. So if I want to draw the point 2, 3 in the xy plane, I'm going to go parallel down the y-axis, and then I'll draw another kind of dashed line parallel to the x-axis. And where they meet would be the point 2, 3, and then 0, or 2, 3 in the xy plane. And then we need to go up 4 in the z direction. So 1, 2, 3, 4, and then we can just go straight up, something like that. And that would be the point 2, 3, 4. This is how I draw in three-dimensional space. Side note, I am not the best artist, but I do my best when I'm drawing things in 3D. So let's take a look at some simple equations. And let's start with the graph z equals 3. Now, you might recall from two-dimensional space, I'll draw a quick little graph down here. If I wanted to draw the line, say, y equals 1, it would look something like this. That would be the line y equals 1. Now, why is it a line? So if I'm in the xy plane, and my function contains only one variable, we're implying that it's true for all of that other variable. That is, when I say y equals 1, that's for all x. We don't write that down, but that's what we mean. So similarly, if I'm in three-dimensional space, and let me plot my x, y, z, or at least write them in again to remind us where the x, y, and z are. When I say z equals 3, this implies for all x and y. So when we leave off a variable in a certain dimensional space, it's true for all of that variable. So here's how I would draw something like z equals 3. I'll just go up to z equals 3. I'll put it right there. And I know it's that height, but all x's and y's at that height. So it ends up being a plane. Something along these lines. But extending in all directions in the x and y. So like y going both the positive direction and then the negative direction, x also going, that's the negative direction, the positive direction. So z is a plane, exactly 3 above the xy plane. How about the equation, and let's do x squared plus y squared equals 4. X, y, and z again. I'm going to add a little bit more detail to the graph. So generally speaking, we use solid lines to draw the positive axes. And then if we wanted to draw the negative axes, we usually draw these as dashed lines in the opposite direction like that. So sometimes I'll draw them, sometimes I won't. But how would I draw the graph x squared plus y squared equals 4? Well, since I'm leaving off the z, that's implied it's for all z. And in case you haven't seen this notation before, let me introduce it to you. When you see an upside down A, in math that means for all or for any. Well, let's start with the graph x squared plus y squared equals 4. Well, this is a circle centered at the origin that has a radius of 2. So let me draw a circle centered at the origin in the xy plane with radius 2, and I'll just try to estimate it, something along these lines. Imagine that's lying flat in the xy plane. But then I have a circle just like that at every z value. So I could extend my graph upwards and I could extend my graph downwards forever, but we'll just draw kind of a portion of it. And then let me make some of these dashed lines solid to get a little bit better feel. Something like that. And what we end up with is a cylinder that surrounds the z-axis, just like that. Well, how about distances in three-dimensional space? Let's take a look at something like this. So let's say that I have some sort of point right up here, and then I have a distance from the origin to that point, just to make it simple. And we're going to call that distance rho. That is the Greek letter rho. It's what we very often use. Well, how could I find that distance from the origin? Well, let's drop this down, pretend like it hits somewhere over here in the xy plane. And I'll draw some more detail for us. And I'll also put in some right angles. So it might not look like it on your screen, but I want to indicate where the right angles would be. So there's a right angle there in the xy plane. There's another one over here that I would normally not draw, but I'll draw it over here as well. So it looks like a parallelogram, but it's really a rectangle. And then we have a right angle going up from the xy plane to the z. So what is this distance rho? Well, let's start by finding the distance from the origin to the point in the xy plane, and we'll call that r. So that length is x, this is y, and then this length up here is z. Well, Pythagorean theorem tells us that r squared equals x squared plus y squared. We already know that. But notice here, and I'm going to redraw my right angle. There's a right angle here that goes above the line R up the z-axis to the point at the top. So there's a right angle there as well. So we can do the Pythagorean theorem on that too. And the Pythagorean theorem says that rho squared equals r squared plus z squared. And then substituting in, we see that rho squared equals x squared plus y squared plus z squared. In fact, if we had more dimensions, we could simply add on more squareds to get like a fourth dimension or a fifth dimensional distance. But since we're dealing with 3 dimensions, this is a 3-dimensional distance, which is simply the extended Pythagorean theorem. Let's finish this off. I'm not going to draw the picture, but I just want you to have this here, which is the equation of a sphere. Just like a circle is a set of points that are equidistant from some center in a plane in a 2-dimensional figure, a sphere is a set of points that are equidistant from some sort of center in the xy plane. So pretend that our center is the point HKL, and then the radius, that is the equal distance, is rho. Well, if you realize that the equation of a circle is really the Pythagorean theorem in 2-dimensional space, it's very similar in 3-dimensional space. We're just going to shift the center here, and we get that the equation of a sphere is x minus h squared plus y minus k squared plus z minus l squared equals radius squared or rho squared.